Okay, good afternoon, everyone. Welcome back to the final session of today. And to kick us off in this session, we've got a remote talk from Victoria Vollmer, who's calling us from the University of Kent. And is going to be talking about a mixed linear and graded logic. Victoria, the floor is yours.
Okay, thank you. I'm Victoria. I'm a first-year PhD student at University of Kent, and this is joint work with my supervisor, Dominic, a fellow PhD student, Daniel, and also Harley from Augusta University. So there's a bunch of us on here. And then this is also work in progress. So the goal is just going to explain the story and kind of point out some interesting things that we've been noticing and maybe some, I don't know, insights that something like a problem that might be an insight. Okay, so like most stories, this story is going to start off very familiar story about capitalism and hunger. So you're working late. You go into the basement of the department and you go to the vending machine and you put your coins in, and food comes out and the coins don't come back, which is, I don't know, devastating. So you think, okay, well, you have money, you have this machine that takes money and outputs food, you have food. Regular logic, you should be able to, get food and money. But this is linear logic, which takes care of resources, so there's no more money. The money got used. So in linear logic, we don't have structural rules like contraction, so two piles of money can't just become one pile of money, which I guess in some sense is good. But you also can't just pull things out of nowhere, so you can't reach into your pocket and pull out some Legos that you didn't have before. But can bring structure back with a bang, literally. So we have these modal operators, and I'm just going to focus on bangs, so this is going to be like rules on the left, that can bring back a more controlled version of these structural rules. So you can have contraction, you can have weakening. And in this example, I don't know if anybody picked up on it, but the vending machine does disappear the second you use it, so it just vanishes. I like to think of bang as like drilling a hole and tying a string to your coin. You can put the coin in, pull it back out, and use it as many times as you want. And I assume most people are very familiar with linear logic, which is why I'm such a fast and like high-level overview of it. Okay, so to get to the more interesting stuff. How fast am I going? I don't know when I started. So intuitionistic linear logic is the internal language of a symmetric monoidal closed category. And then you can think of this modality. Modalities add structure, so that's always going to be monads, comonads. We're dealing with just the ones on the left, so it's a comonad. And so you have this little picture, and we're going to specifically think of linear exponential comonads, so they have a little bit more structure. This is stuff from the, this is all building up to Benton's work, so this is the way that they did it in those papers. So then if you remember this fun little fact, or this, given an adjunction, you can make a comonad, you can do that backwards, and this is the basis of Benton's linear nonlinear logic. So you have that picture, we have the symmetric monoidal closed category. You have the little comonad, but now the comonad split into an adjunction, and on the other side of the adjunction is a Cartesian closed category. One way to think of this is that there's an interpretation from intuitionist logic into intuitionistic linear logic, and there's an interpretation of intuitionistic linear logic into intuitionistic logic. So they kind of mutually interpret each other. And then this is the linear nonlinear logic that Benton came up with. It's very, very great. Definitely recommend reading this if you haven't. So on one side you have the regular intuitionistic logic, where you always have access to structural rules like weakening and contraction. And then on the other side, you start with this like assumption of linearity, and then you also have the ability to have nonlinear things as well. And going around back and forth should be, that's the bang operation. So this adjunction forms the comonad. Okay, so now that's the setting of the story. That's the the universe that we're in, and now we get to meet the main character of our story, which is graded modal logics. So as we saw with linear logic, we bring these modalities in to get structural rules back into our logic. But sometimes you want something more than just, two piles of money smashed together and as one pile of money. You want, to keep track of this, a more fine-grained approach. So you can look at these modalities and you can index them by elements of an algebra, and the structural rules correspond to these algebraic operations inside of the algebra. So the example here of your 2 piles of money can now become 1 pile of money, but you don't lose the amount of money. 5 coins and 5 coins now becomes 5 plus 5 coins, right? Okay, I assume everybody is perfectly paying attention. Okay, so we want to do the same story that Benton did, where you have these 2 logics on 2 sides, and you can move between them. They mutually interpret each other. But what would that mean in the graded world? What are the 2 graded logics that we're going to look at? So the one where we always have structural rules, the one that's like the equivalent to the intuitionistic logic, where you always have weakening, always have contraction, is where we just assume everything has a grade. And you can always use structural rules by always applying this like algebraic aspects of the grades. So you can always do weakening, always do contraction, always do exchange, those sorts of things, right? So that's, you have your formulas, your types, and then these are like, this capital delta is, your context, and the lowercase delta is a grade vector where each one of these grades is acting on, is like indexing the term. Okay, and then the other way is if you start with the assumption of linearity, and then you just say, okay, and sometimes you have this graded modality. And these actually correspond to two ways people have been doing graded modal logics. And so one is called graded base, and the other one people refer to as linear base. So you assume you have linear and then you add a grade, or you just assume everything is graded. And we want to kind of combine these together. So put them on one slide, and we want to be able to go back and forth between them. So we want to do that with these 2 new modal operators called linear and graded, where linear takes a linear thing and it brings it into the graded world, and graded takes a graded thing and it takes it to the linear world, right? So those are the main characters right now of our story. So these should form the 2 parts of the adjunction. That's what we want. So we should start thinking about how to make that work, right? Because we have it in the logic and now we need the math to work. So the first thing to do is to make sure that, when we build this comonad, all the types work out. So we need some background math. So we're looking at the structure of the comonad. So we just take a regular, we just box, and then we want to look at the free coalgebras, right? And so this delta here is the important one. So we'd think that the free coalgebras would look like this box R, A, and delta. And we'd expect that delta would have this type where it takes box RA to box RA. But we saw in the previous slide that it doesn't have this multiplication aspect. So this would only work if our multiplication, R times R was always R, which isn't true. Because we're being very general, you can use any algebra. So instead of just doing this way of trying to find these coalgebras so that we can get the structure, we're going to kind of change our expectations and come up with a different way of coming up with these coalgebras, which is to look at, change the base category that we're looking at and change our expectations, right? So instead this, if we look here at the F coalgebras for a functor of this type here, this would be easier if I could point to it. Then the expected type that we care about is this one down here, for these families of morphisms instead of just that. And then if we plug everything in, I have no idea. Then, okay, so if we look at this box comonad again, then if we do this sort of partial evaluation of it, then the type of this box blank A is the right type, and then delta blank blank A is a family of morphisms, and that actually has the right type as well. So everything works out, and this is all work from this paper here that's cited. So this tells us that the base category we have to work with isn't just you know, normal. We have to kind of be thinking about this in this category of coalgebras that we built this way. If anybody knows, this is the Eilenberg-Moore category, where you think of this as like a lax functor. I did not look at my notes for that. So hope I said everything correctly. Okay, so we want to think about now that we have this structure of a comonad, we can have we have one side of this adjunction. Maybe we can just do the adjunction as is. So we're going to think about this one going between the Eilenberg-Moore category, so the coalgebras, and this symmetric monoidal category. And what happens if we just think, what is this adjunction? Does this give us what we want? And we have to remember the goal is for this way and then that way on our adjunction, a little roundabout, to give us box R. But if we work out the math, it's always box 1 and not box R. No matter what the R is, we lose the grade. So the way to fix that is to use this strict action, which takes this R and it sort of inserts itself with multiplication into the structure here. Okay, so then we can, if we just have this, use this action here, we work out the math, then we get to keep the R. So that's one way that we can we can keep the grade. So the two things we learned is that the base category we have to work in has to be this category of functors, and that we need the strict action to be able to keep the grade. Okay. So then we can use this fun fact. This is also, I think, from Shinra paper. So symmetric monoidal adjunction plus a strict monoidal action gives you a family of adjunctions. This is a slide from a previous talk that I just really like, that shows, this is my picture of what is happening here. You know, you have your normal adjunction picture, which everybody should think of as, you know, a little map in trains. But the action splits this up into a family of adjunctions. Okay. That picture make any sense to you? No? Okay. All right. So that basically gets us everything, like the state of the art, and how everything is. And so our job from here should just be to glue these ideas together and write some proofs. Everything should be set up really nicely. But when we start to go to actually do things, we start to, you know, make the obvious decisions. We're doing very syntactic things. So the obvious decision for us is use these graded multi-categories. So use multi-categories because we have these big contexts, and just do grades to them. And this is where the cracks kind of start to appear, which can be a good or a bad thing. For me, I'm an eternal optimist, so cracks are a way to look down and see something maybe deeper happening. So here, the first thing to notice is that the way that we did the multi-category, this list structure for the context is baked in, and we're thinking about structural rules and how to manipulate context. So having this baked in structure is a little bit of a warning sign that something might go wrong up ahead. And so I should actually define what these graded multi-categories are. So graded multi-category, you have your objects and your algebra, and it's just like a regular multi-category where you have list of inputs for your multi-arrows, but this time each of the inputs is being acted on by something from this algebra. Okay. And then, so this is where you can very, very well see the cracks of this list aspect when we start to define structural transformations. We want to be able to control structure, we want to talk about structures, so we should have these natural transformations to talk about structural operations in our multi-category. And so we have just rules for weakening, right? So you can add something to your context, and there should be a natural transformation from that arrow to the one where you added something in that context. But to express that, we have to be very precise with these indices because of this like list indexing that's kind of baked into the formulation of multi-categories that we used. So I'm not like a huge fan of the way this is presented. So you can see these indices when you're trying to write an actual proof, trying to prove like complicated things about the interaction of these structural rules and how they like move around between each other. They become absolute nightmares. So, especially since composition in a multi-category is already very messy, and there's not like great ways to draw out or work through things. So that gives me like a lot of thoughts that maybe what we need to be doing is looking more into better ways of visualizing things. So for me, I think we should be working with something that lets us work on multiple levels, because like something like string diagrams, because we're working on these natural transformations, and then we also have the multi-category, and it's based off these like categorical algebras. So something like that lets us visualize multiple levels and work through proofs would be very useful. But right now, we just have this messy index nightmare. Okay. Yeah, so that's the, oh, I'm going so fast, aren't I? So that's the start of everything. So, okay. Now that we have a definition of our categories that we're using, and we know how to make the adjunction, we can just build these models. So what we do is we start with a LNL model where both sides are multi-categories, and then we make the Cartesian closed category one into a graded category, multi-category, and then we have this adjunction, where we use this strict action, and I can expand this definition out. So we actually use the adjunction, the original adjunction from the LNL model to define ours. So because we also take advantage of the fact that this X in our category is a functor, and so now this is how they're defined. Oh gosh, okay. I really want to point to things, but you can't see my fingers, so I'm very sorry. So yeah, so this is, I went so fast because I'm very nervous. I'm sorry. So this is basically the end of, we have a bunch of theorems that are mostly proved. Some of them are conjecture still. You know, for the logic, we obviously have stuff like cut elimination, and we have soundness with respect to the cut reduction. But when it comes to the actual proofs, they're very messy, and the interpretation is also extremely messy. So that's like the state of the art here. Is we thought we did something very obvious, and we ended up with something that was almost impossible to visualize and to show other people, which showed us that there might be something much more like deep, like something deeper happening, where the tools of abstraction we need are much more sophisticated. And yeah, so that's everything. Sorry I went so fast.
Okay, thank you, Claire. We're in danger of being back on schedule, so I think we should have some questions. Any questions from the audience? Alex,
So I need a microphone.
I'll just repeat your question, sure.
So my question is going to be, can you do this construction with any such R? So the type of the grades, and if so, can you have like an infinite element of R that recovers what the bang was doing?
So the question is, can you use any R? And if so, can you have an infinite element in R which recovers bang?
Yeah, I think there's work where people have recovered. It's not like the most elegant solutions for these graded modal logics, but people have recovered. I'm pretty sure, yeah, they got bang back. The problem isn't so much with regular bang; it's the push when you push through the tensor, you end up with some issues. So, there's a paper. If you message me later, I can find the citation and send it to you. I can't remember off the top of my head. Sorry.
So a quick question for me, when I was watching the graded part of it, it did remind me a lot of quantitative type theory from Bob Abke and people like that. Is there a relationship? Can you say anything about that?
Yeah. There's a relationship. I don't know if there's much more to say other than yes, they're in the same like aisle in the grocery store. They're like
Okay.
different flavors of the same product, I guess.
More questions?
Okay, the last one for me then. You mentioned string diagrams as a good as a candidate for a different syntax, which seems to me like a great idea. Do you have any thoughts about what that would look like more concretely, or are you just beginning thinking about it?
Yeah, so there's only one hiccup that we have, which is that we're working with multi-categories and we're not like fully, well, I'm personally not fully set on our formulation of multi-categories, and I don't even know what string diagrams for multi-categories would be like. So that's the only hiccup, but in general, string diagrams look really perfect for working with these adjunctions and like categories of coalgebras and all these like the same sorts of constructs that we use are the same ones that show up a lot when you look up like even introductory things for string diagrams.
Okay, well, at the risk of tooting my own horn here, in my PhD thesis was about proof nets for polycategories, which is like the both sides multi-version.
Yes.
So it turns out to be really easy. So.
Oh yeah. Okay. I will look that up. My goal here is for people to tell me what to look up to make the math less hard, I guess. More beautiful. I have a very strong aesthetic preference for math, and indices are not where it's at.
Okay, last chance to ask a question for the audience.
Are there additive available in this topic, or they be added?
The question is, what about the additives?
Oh, it's just the like a monad. I think it's just the flip of it. It's just not the side that I was working on, so yeah, it's just the right, it's just flipping instead of it being bang, just work with the on everything flips. Isn't that right? I don't know.
Yeah, so on the CCC side. Okay, let's wrap it up. So thanks very much, Victoria.
Thank you.
Press the question buttons.